Welcome to this explainer on teaching computers to learn. Let's just kick things off with a quick thought experiment, okay? Imagine showing a toddler a golden retriever and then a German shepherd. Despite the massive differences in size, shape, and fur, their brain effortlessly generalizes the concept of a dog. They just know it, instantly, with zero explicit rules needed. So how did they actually pull that off? Well, the child basically performed advanced pattern recognition and generalization. From the very day we're born, our brains are just constantly collecting data, adjusting for errors, and getting better. And, for thousands of years, this extraordinary biological capacity to generalize from experience, that was exactly what distinguished human intelligence from machines. To really understand why this concept sparked such a massive revolution in computing, we've got to contrast the old way of doing things, writing traditional, rigid rules, with the modern approach, which is all about providing examples. For decades, computers were absolutely brilliant at calculating and automating heavy workloads, but they relied entirely on human programmers to literally map out every single logical step. Think of traditional programming like a super strict recipe for making tea. You boil the water, place the tea bag in a cup, pour the water, wait 3 minutes, and serve. The computer blindly executed these steps. It never improvised. And honestly, this rigid step-by-step execution is exactly what built the early information age, right? It automated our bank accounts, factory pipelines, and payrolls at lightning speed. But here's the catch. Relying purely on strict rules inevitably makes things incredibly brittle. Imagine trying to write a program to recognize a dog using rules. You type in, has 4 legs, has 2 ears, a tail, has fur. But wait, what if the dog is viewed from the side? Or what if it's hiding behind a chair or covered in snow? The system instantly breaks down because you simply cannot manually code for the infinite edge cases of reality. You just end up with a massive, unmaintainable mess of code. When faced with all the crazy, infinite variations of the real world, like the nuances of human slang, sarcasm, or just visual clutter, traditional programming hits a massive brick wall. So researchers completely pivoted away from trying to write all these rules. Instead, they asked this incredible, paradigm-shifting question: what if computers could just discover the rules themselves? This historical pivot is absolutely fascinating. Back in the 1950s, an IBM researcher named Arthur Samuel was working with these massive computers that took up entire rooms, but had way less power than the smartphone in your pocket right now. He decided to teach a computer to play checkers. But instead of programming every single possible move, he wrote software that just let the computer play the game over and over. Now, it made terrible decisions at first, obviously, but after thousands of games, it actually learned from its mistakes and started identifying winning strategies. In 1959, Samuel basically coined the term machine learning, defining it as the field of study that gives computers the ability to learn without being explicitly programmed. But what does learning actually mean for a machine? It doesn't have emotions, right? Well, it's a lot like a person learning to shoot a basketball. You make a prediction, you take a shot, you miss, you measure your error, you adjust your angle slightly, and you try again. For an algorithm, it's the exact same process. Make a prediction, measure the error, adjust slightly, and repeat. It does this millions of times until it mathematically optimizes the perfect pattern. Now, to pull off that kind of optimization, the machine needs fuel. And that fuel? It's data. Actually, let's be crystal clear. No data equals no learning. Asking a machine learning model to learn without data is exactly like asking a student to pass an exam without ever giving them a textbook. If you only give an algorithm a few narrow examples of a concept, it won't generalize to new scenarios at all. It absolutely needs massive variance to discover those robust, underlying patterns. But you can't just dump raw data into a computer randomly and expect magic. It has to be structured so the machine can actually make sense of it. When we look at the anatomy of learning, we basically break these observations down into 2 critical building blocks: features and labels. Think of features as clues. They're any measurable property that helps describe an observation. So if you want to predict tomorrow's weather, your features might be today's temperature, wind speed, and humidity. Now, individually, temperature alone doesn't tell the whole story. But when you put them all together, these features provide a multidimensional web of evidence that helps the algorithm spot meaningful patterns. Then we have the label, which is sometimes called the target variable. The label is basically the correct answer, the specific objective we set for the machine to predict. For instance, if we're feeding a system real estate features like square footage and the neighborhood, the label would be the final selling price of the house. We provide the features, we give it the label, and let the algorithm mathematically figure out the path between the two.
Let's look at a real-world example to see how this all comes together. Imagine we want to predict dangerous air quality, specifically PM2.5 concentrations during a wildfire. No engineer is sitting there writing a rule that says, okay, if the wind is 10 miles per hour, pollution spikes. Nope. Instead, the algorithm is fed thousands of historical wildfire events. It maps dimensional features like wind speed and burned area directly to the known PM2.5 label. The machine maps those complex mathematical relationships completely on its own. And fun fact, this exact process is literally what powers the air quality warnings on your smartphone right now.
Being able to analyze hundreds of variables at once is incredibly powerful. But, and this is a big but, machines completely lack common sense, which leads us to a pretty famous failure in the AI world. A while back, an AI was trained to distinguish between pictures of wolves and dogs. And it crushed it. It achieved a spectacular, almost unbelievable 99% accuracy. At first, the researchers were absolutely thrilled. But eventually, another team decided to look under the hood. They started asking, wait, what was the model actually looking at to make these highly accurate decisions? When they investigated how the AI was getting it right so often, they realized something absolutely shocking. The algorithm wasn't focusing on the physical traits of the animals at all. It was looking at the snow. It turned out that almost all the wolf pictures in their dataset had snowy backgrounds, while the dog pictures were taken in parks or indoors. The brilliantly complex algorithm had simply learned to detect snow. You see, AI is fundamentally kind of lazy. It will always find the easiest mathematical shortcut. It just optimized for the background pixels instead of the actual animal, a shortcut that would instantly fail out in the real world. This right here is why experienced AI engineers will always tell you that good data is way more valuable than a complicated algorithm. It's the classic rule, garbage in, garbage out. If you feed a system accidental relationships and poor quality observations, like snow instead of wolves, you're going to get poor predictions. Data quality is quite literally the ultimate gatekeeper of artificial intelligence. So as we wrap up this explainer, just think about how far we've come. We're no longer writing those rigid, impossible to maintain instructions. Instead, we provide rich data, we allow machines to measure their errors, and we watch them learn and improve. They're out there discovering the hidden rules of our world right now. And it leaves us with this really fascinating question. Since computers can now discover the patterns of reality from data, as we continue to feed them the data of our daily lives, what new, unseen patterns will they discover about us?